Hello all, I'm Chandra Sekhar Jassti, a graduate student at Florida Atlantic University. Today I'm doing a presentation on a research paper called C-Store, Column Store, a column-oriented database management system. So this is the outline of the presentation which we'll be going through. So coming to the proposal, the researcher of this paper have proposed a column-based store database management system, which is when compared to the row store database management system is better. So coming to what is row store database management system is that in row store DBMS, the attributes of a row are placed continuously in a storage, while in column store, the values for each attribute are stored continuously. The row store DBMS is a write optimized system, whereas the column store DBMS is read optimized system. So the applications of the row store database management system includes OLTP style applications, while column store database management system is best suited for data warehouses, the CRMs, and the ad hoc inquiry systems. So coming to why the column store DBMS, because it can only bring required attribute values into the memory, and its typical queries involves aggregation of important attributes only, and it is easy to encode the column values together, which is of the same data types, and the data can be packed densely rather than aligned by byte or word boundaries. So what is C-store, the column store? It stores a group of columns in the form of projections, which is a distribute architecture where different projections could occupy different nodes, and it supports a key save failure mode, and it has both read optimized column store and an update or insert oriented writable store. So coming to the architecture of the C-store, it supports read optimized workload. It avoids the locking with write based workload. And there are two logical sets. One is the writable store WS, which supports high performance inserts. And another one is the read optimized store RS, which supports high performance reads. And it involves a tuple mover, which moves the updated records from the writable store to the read optimized store. So the continued architecture, which involves the queries in SQL access the data in both the storage system. It means the WS inserts and the RS deletes. So the groups of columns are stored in a physical continuous manner in the C-store DBMS, and they are anchored on a logical table T. The logical table can also contain columns for other tables that are related to this logical table through foreign keys. Example is given in the slide. So tuples in the projections are stored column-wise. The K attributes will be stored in K data structures, and all these data are sorted on a sort key, which is a column or a set of columns in the projection. So coming to what is segments and storage keys. So as said earlier, it is stored in projections. So every projections is divided into segments, which is a value-based partitioning on the sort key. And coming to the storage keys, in each segment, different column values which belong to the same record are identified by the storage keys. So consider a table T which has two projections T1 and T2. A tuple in the segment T1 will have corresponding join index called SK, where S denotes the segment ID, SID in the projection T2, and K represents the storage key of the corresponding tuple in the T2. So maintaining the join index is expensive since any update to the projection leads to an update of incoming or outgoing join index. So hence each column is stored in several projections. Coming to the read optimized store, it follows four type of encoding schemes. One is the self order with few distinct values. Second one is the foreign order with few distinct values. Third one is the self order with many distinct values. Fourth one is the foreign order with few distinct values. Coming Coming to WS, which is the writable store, it is similar to the physical structure of the readable optimized store. To avoid writing query optimizers differently. The difference being columns are not encoded since it is assumed that the WS is trivial in size when compared to the RS. It also ensures efficient updates. The sort keys are represented as pair S comma SK, and every column represented as V comma SK, and a B tree is built for SK. Now, how the storage management works in C store. A storage allocator will allocate segments to nodes in a grid system. It co-allocates the following with same columns in the projection and same segments of RS and WS. So coming to the updates and transactions in the C store, node is responsible for creating a new storage key for the entry. Then it is given a unique storage key, which is a combination of node ID and the local counter. So locking is minimized using snapshot isolation. So coming to what is snapshot isolation, as said earlier, it stores in projections. So every projection segment in WS has an instruction vector called IV. So IV has epochs or time ranges at which records are inserted. And every projection has a deleted record vector as well, which is represented by DRV, which contains the deletion status, and a high watermark, which denotes the time at which snapshot isolation ran, and a low watermark, which indicates the latest time at which a read-only query can be run on the snapshot. So the figure here shows how the snapshot isolation works with site 1, site 2, and site 3 with decreasing in time. So coming to read-write transactions, each transaction gets a master. The masters will split the work of the transaction and assign it to the appropriate nodes. So once all the nodes finish their work, the master will send a commit message. It releases logs and deletes and the undo log. So as supported earlier, the C store also supports the recovery, which is the key safety. So the K sites can fail in time to still keep the transaction consistency. If a failed node has no loss of data, it can be rectified by using updates that will be queued for it elsewhere in the network. So suppose if both RS and WS crashes, the segments will be reconstructed from other projections and joined indexes in the system. So WS getting damaged is a common case. So the first step in that cases would be to check if it can be retrieved completely from other projections. So if the common case becomes otherwise, the authors of the paper have proposed to make the tuple mover log all the information it moves to the RS. So coming to what is the tuple mover. So tuple mover moves the blocks of the tuples from WS to RS segment. The records deleted before the low watermark are ignored. The rest were moved by creating a new segment in the RS with the updated data and then deleting the older version of that segment. So each tuple gets a new storage key and the segment ID, and join indices also need not be maintained. So coming to the performances of the C-store DBMS, the authors have implemented only a single site read-only queries. They have used a simplified version of the TPCH benchmark with 7 queries, and they have compared the performances of the 3 systems, each with a storage budget of 2.7 gigabytes. So as you can see, the disk usage and the query execution time for the relational schemas is represented by the left table, whereas the materialized schema is represented by the right table. From the table, it is clear that the C-store DBMS have performed well when compared to the row store DBMS. So the performance can be summarized as shown. The C store is much faster than either commercial product. It is because of the column representation, which avoids reads of unused attributes. It stops storing overlapped projections rather than the whole table, which allows storage of multiple orderings of a column as appropriate. It has better compression of data, which allows more orderings in the same space. It has query operators to operate on compressed representation, which mitigates the storage barrier problem of the current processors. So to summarize, the authors of this paper have proposed a concept of read-mostly databases, which is a hybrid architecture that permits column store transactions. And they have tried to do an experiment which emphasizes on compressing the data and coding the data values to save space, and meanwhile storing the representations of the data on the disk. And they have proposed a data model which, instead of usual tables or secondary indexes and projections, consist of overlapping projections of tables. And they have made use of effective use of isolation of snapshots. So these are the references which they have taken while publishing the paper. So thank you.